All right, so we're finally coming down to the question of if power series are actually functions, what values of x are we allowed to evaluate those functions at? In other words, what we're getting at is what is the domain of these particular power series? And just as a hint, we're going to do some ratio test coming forward. So let's make this a little more explicit. Consider the following power series that represents some function f of x. This power series is equal to, say, the series from n equals 1 to infinity of x minus 3 to the nth power all over n. And again, just so we're on the same page, what we're asking is, what values of x make this power series converge? And that's the same question as asking, what is the domain of this power series? What values of x are we allowed to put into it so that we're given one finite output back? So let's take a look at this power series. Now, the way we could try to approach this is, say, choose your favorite x value. We could try, say, x equals, 7. So we consider this function, f, evaluated at x equals 7. We plug in 7 everywhere there's an x. So this would be like 7 minus 3 raised to the n all over n. And then we ask ourselves now, well, for this series, does this converge? Does this diverge? So again, just doing out a little bit of algebra here. This will be a 4 over n all over n. Hey, does this converge? Does this diverge? And then after that, we could try a different number. Say x equals minus 1 over 10. So when we plug that into our function, x equals minus 1 over 10. And we consider the resulting series that comes from that. And now notice, these series are actually all starting at n equals 1. Just the way I defined it above. So if we plug in negative 1/10, well, that's negative 1/10 minus 3, that all raised to the n all over n. And then we have to figure out, hey, does this converge or diverge? And you know what? This method doesn't seem too good because we're literally saying I get to check values between negative infinity and infinity. And if I try to figure out, what the domain is of this power series, just by testing out random values between negative infinity to infinity, this is not going to be a good way to go. So again, we have a power series. We could try just guessing different values of x, seeing if it converges or diverges, but this is going to take us probably for the rest of our lives to figure out when these power series actually converge or diverge. So let's go back and revisit the original series, or the original power series. And let's see what we notice. Well, in this original power series, we have some number being raised to the nth power. We have an n that's by itself to the denominator. So we have an n to the first. All right, whatever is in that denominator. The thing I want us to focus on is this x minus 3 raised to some power. This looks like what we have is a constant raised to the power of n. If I tell you an x value, so in other words, this looks like we have a constant raised to the power of n. If I say, hey, let x equal 7, let x equal minus 1/10, we're going to get some x value raised to the power of n. And what this tells us is this was one of the functional forms that we get to use ratio test for. So whenever we're handed a power series and asked, hey, How can I figure out what x values it converges, for which it converges? We get to do ratio test first. So if you remember, as a quick aside, what ratio test was if we're given a series, we would take the limit as n goes to infinity of the absolute value of the next term in the series divided by the current general nth term of the series. And there's three things that can happen. When this ratio is less than 1, our series is absolutely convergent. When this limit is greater than 1, it suggests our series is divergent. And the third case was when it's equal to 1, it's inconclusive. So that's just a quick refresher on ratio test. We're going to apply ratio test to our power series. And what this is going to do is hopefully take this negative infinity to infinity kind of possibility of what x values we could evaluate our series in, and try to narrow it down into some smaller region in which the series converges. That's our goal with ratio test here. Basically take this minus infinity to infinity possibility and really narrow it down into some region that could make this series converge. So let's go ahead and apply ratio test. So we take the limit as n goes to infinity of the n plus first term in our series, which will be x minus 3 raised to the m plus 1 all over m plus 1, and then we divide that by the general nth term, which is x minus 3 raised to the n all over n. And again, since we have this quotient of fractions, we reciprocate that denominator and multiply, and we can combine similar types of functions over one another. So this would be x minus 3 n plus 1 all over x minus 3 to the n times an n all over n plus 1. And from here we want to try and reduce as much as possible just using algebra. So we see we can cancel out a whole factor of x minus 3 to the n out of that numerator. So in that numerator, we're just going to be left with one factor of x minus 3. And this other term, n over n plus 1, it looks like we could be stuck with that. There's no shortcut of algebra there. So what we actually have is now the absolute values of x minus 3 times this n over n plus 1. And I want us to notice something right now. This limit is with respect to n. This term here has no n's. So what we could actually do is just pull it right out of this limit. And again, we have to keep the absolute values though. So this is absolute value of x minus 3 times the limit as n goes to infinity of the absolute values of n over n plus 1. And this limit, after doing a L'Hopital's, just equals 1. So at the end of the day, what this equals is just the absolute value here of x minus 3. And remember, for ratio test, in order for a convergence, we need this to be less than 1. So I'll just write a little note for convergence. So this inequality that I'm introducing right at the end, I am putting there because we want this series to converge. So we want this inequality to be less than 1. And this inequality now is actually what's going to tell us a bunch of x values that work. In other words, it's going to tell us a lot about the domain. So let's go ahead and do that next. So we have x minus 3 is less than or equal to 1. This is what we need to solve to figure out what the domain looks like for our power series. And well, to do this, since we're dealing with an inequality, in absolute value, there's two things we get to do. There's sort of the forward thing where we just take x minus 3 less than 1 and we solve that inequality, which we can do right away. So we get that x must be less than 4. But the other side of things is we have to take, well, the negative of that when the quantity x minus 3 gets multiplied by minus 1. And then we're looking at this, well, that has to be greater than minus 1. And that sign flips because we multiply both sides by minus 1. So we're really solving, in this case, x has to be greater than 2. So again, what this domain looked like for us. Originally, we could try any x value from minus infinity all the way to infinity. And what we're finding now is, well, it looks like x values when x is greater than 2 and less than 4, these x values seem to work for this power series. And now notice, I'm not using square brackets. I'm only using rounded brackets here because, again, this inequality doesn't work, or we don't get out of ratio test what happens at those endpoints. So ratio test doesn't tell us what happens at x equals 2 or x equals 4. So ratio test basically narrowed down from minus infinity to infinity this region of x values between 2 and 4, which give us a convergent power series in this case. But it doesn't tell us what happens at those endpoints x equals 2 or x equals 4. For those endpoints, we get to test those endpoints individually. So let's go ahead and do that now. So if we test the x equals 2 endpoint, we again go back to our original power series. We plug in x equals 2 into that power series. So the series we're looking at for testing for convergence is now the series of minus 1 to the n all over n. And well, this is an alternating series, so we can apply alternating series test. And if we apply alternating series test, we take the limit of all the positive terms in that series, not including the minus 1 to the n. So that's just 1 over n in this case, and that limit as n goes to infinity is 0. The next thing we get to do is just show that the terms are decreasing for the alternating series test. And in this case, well, if we have the next term in the series, and we have the current term or the previous term, we can see, well, the numerators are the same, directly comparing the denominator. That right-hand side is larger than the left-hand side, so the terms are decreasing. So at x equals 2, the power series converges. So if we go back to the values that make the power series converge, we now have that, well, at 2, it is less than or equal to when x is greater than or equal to 2. But the verdict is still out on what happens at 4. So let's test x equals 4 next. So again, we're testing the endpoint at x equals 4. So we plug x equals 4 into the original power series that we're given. So this is 4 minus 3, all raised to the n over n, which in this case gives us a series from n equals 1 to infinity of 1 to the n all over n. And well, 1 raised to any integer power n is just equal to 1. So this is just the series 1 over n. And this series is harmonic, so it diverges. Or we could also say it's a p-series with p equals 1, which is less than or equal to 1, so it diverges that other way as well. So the x values that are allowed in our power series are the following. So between 2 and 4, our x could be greater than or equal to 2, but it strictly has to be less than 4. That endpoint at 4 doesn't give us a convergent power series, whereas that endpoint at 2 gives us a convergent power series. And this interval here is what we call the interval of convergence. If I could spell it right. So that's what we mean by interval of convergence. Basically, it tells us the domain or the x values in which we're allowed to evaluate that power series at. For one other little piece of a definition mathematically, if we go back to our inequality, whenever we have an inequality that looks of this form, where we have x plus or minus wherever it's centered at, less than some right-hand side, that right-hand side is what we call the radius of convergence. So in this case, our radius convergence was equal to 1 for this example we just did. And I want to emphasize, for radius convergence, all we care about is whenever we have this absolute value of x plus or minus a number. We don't have 2x plus or minus a number, or x over 3 plus or minus a number. We just have a coefficient of 1 on that x, plus or minus a number, less than whatever that right-hand side is. So the big takeaway I want us to say from this example the first thing is we use ratio test to see when the power series converges. And again, ratio test doesn't give us everything, but it gives us a bulk of that interval. It just doesn't tell us what the endpoints does. So after we apply ratio test, we test the endpoints individually. And the third thing that I want us to just notice was the limit is always with respect to x. Or sorry, the limit is always with respect to n. In the ratio test. So if we have terms that don't depend on n and they're being multiplied onto the rest of that limit, we could pull them out in absolute values, just like we did with that x minus 3 term. All right, so in this case, we again saw that ratio test narrow down this minus infinity to infinity possibility of x values into some very small interval of convergence. Let's do a couple more examples. So here's another power series. This is the function, or the power series, from n equals 0 to infinity of n factorial times x to the power of n. And again, we care about what x values give us a convergent power series, or what is the domain of our power series. So the first thing we note is, well, we have x raised to some power of n. That's a flag for us to use the ratio test right away. Just as a little bit of review, we also see we have that n factorial, which also suggests, hey, use ratio test. So let's first apply ratio test onto this power series. So we take the limit as n goes to infinity of the next term in the power series, n plus 1 factorial, times x to the n plus 1, and we divide it by the current term, or the nth term, which is n factorial, times x to the power of n. And, well, hopefully you remember how to do a little bit of factorial algebra. We could rewrite this n plus 1 factorial as n plus 1 times n factorial, and we see that those n factorials from the numerator and denominator will then cancel out. Similarly, we can also cancel out a factor of x to the n out of both terms in the numerator and denominator to be left with an x to the power of 1 in the numerator. So let's rewrite what this limit looks like. So this limit looks like the limit as n goes to infinity of n plus 1 times x. And again, this limit is with respect to n, and that x term has no n dependence, so we could pull that out of the limit. So we pull it out in absolute values. And then we just have the limit as n goes to infinity of the absolute value of n plus 1. And again, if ratio test is to converge, we need this to be less than 1. And welp, this thing is surely going off to infinity. So how could we have this limit, or this product of absolute value of x times this limit being less than 1? And well, the only way that happens is if x is identically 0. Again, not approaching 0. If x is just identically 0, well, then this right-hand side or this left-hand side just equals 0. Again, it only gives a limit less than 1, though, because the product of this entire thing coming from the original limit is identically equal to 0. So in this case, this series only converges when x is identically equal to 0. But what does that mean? Well, let's go back up to our original series. If x is equal to 0, well, then our function is just f of x, or f of 0, is equal to 0. So the only value that works is one particular value of x, and that value being the value x equals 0. No other values of x will work because this limit from ratio test blows up to infinity. All right, let's do another example. For this example, let's remember our friend, the Bessel function of order 0. And again, for our considerations here, there's no reason you should memorize the Bessel function of order 0. This is just to say that when we have these ugly-looking power series, we can actually do these operations on power series in the similar way to we've done for the easier-looking ones or the more difficult-looking ones as well. So again, what we care about is what x values, or what is the domain, or what x values give us a convergent series here. So if we look at this again, well, we have x raised to some powers of n. Again, that's suggesting we don't know what x should be. X could be 2, it could be 1/3, it could be 17. We can just see that that is then some number being raised to n power stuff, so it's suggesting ratio test. But just as review, we also see factorials, and we also see other constants being raised to powers of n, which also suggests ratio test for us. So let's hit this with ratio test. All right, so we take the limit as n goes to infinity of the absolute value, the next term in the series, -1 to the n plus first. We have x to the 2 times quantity n plus 1, all over 2 to the 2 times quantity n plus 1. Parentheses are really important here. And finally, we have n plus 1 factorial, that being squared. That is all in the numerator of that series, or of that limit, times the series function that we have. So this looks like a really ugly limit. But again, this is the quotient of two fractions, so let's reciprocate and multiply. And then again, combine fractions that have similar looking terms. So we can write this as a -1 to the n plus 1, all over a -1 to the n. This term in the numerator, since we have the product in that power, this is really an x to the 2n plus 2. We're going to divide that by x to the 2n. Next, in that denominator of the top fraction, we have another multiplication of powers. So this just looks like, well, a 2 to the 2n plus 2. And then what's going to sit on top after we reciprocate and multiply is that other 2 to the 2n. And then finally, we have all that factorial business. Well, if we have n factorial squared, that is really n factorial times n factorial. And if we have n plus 1 factorial squared, that is n plus 1 factorial times an n plus 1 factorial. All right, let's not forget about that absolute value on the edge. All right, so we did it so far. Well, that absolute value, speaking of which, will cancel out any negative signs that we get, so those negative terms will just go away for us here. Or we're just left really just with a -1. But again, since that doesn't have any independence now, we could just pull it out in absolute values, and the absolute value of -1 is just going to give us that +1. All right, let's do some more simplification. We can cancel out a factor of x to the 2n out of the numerator term. And then if we do that, we're just going to be left with an x squared. Similarly, we can factor out a factor of 2 to the 2n and cancel out that 2 to the 2n from the numerator and denominator. And we're just going to be left with a factor of 2 squared. And for each of these factorials, we could write each of these n plus 1 factorials as an n plus 1 times n factorial. And then we'll see that those n factorials will cancel out those n factorials from the numerator. So let's see what we got. Cleaning up this limit, we have that this is x squared in the numerator. We have a 2 squared in the denominator. And the only other terms that survive were the 1 over, now the quantity n plus 1 squared. And well, all of the n dependence is over on this n plus 1 quantity squared in the denominator. And as n goes to infinity, well, this entire thing is going towards 0. So what does this tell us? Well, again, for ratio test, what we want is that this limit is less than 1. Well, the limit is always less than 1 because it's equal to 0. So what this tells us is, well, it doesn't matter if I put in, say, x equals 1, x equals 736, x equals minus 10,037. Any x value is going to work and give us a convergent series because that ratio test limit is always equal to 0. So in this case, any x value works. So if any x value gives us a convergent power series, what that means is the interval of convergence would then be minus infinity to positive infinity. Again, any x value works. And what the radius of convergence would be r equals infinity. Another way to think about the radius of convergence And the interval of convergence is if we're sitting on the number line, and we're seated at A, where the power series is centered. The radius convergence tells us how far we can reach our arms and still get convergent values or a convergent series. And the interval of convergence tells us explicitly, basically, hey, when we're reaching our arms out, what x values am I allowed explicitly to plug in? Are these x values including the endpoints, or x values not including the endpoints? Or one x value or one endpoint we include, one endpoint we don't. So at this point, we figured out, okay, we have these power series. We can differentiate them. We can integrate them. We can even figure out what x values would lead to convergence of these infinite sums for us. Again, what is the domain of these power series? But what we actually need to know now is what functions are getting represented by these power series. And that's what we're going to turn our sights to now. How to represent functions that we may know using power series. Check out the next series of videos.